In this video we're going to take a look at a challenge from ImaginaryCTF, which, unlike the competitions you see on CTF Time that run for a few days or a weekend or something, this runs all year round and there's a new challenge released every day. Once you solve the challenge, you can submit the flag in the Discord and then you can go and have a look at other people's solutions for that challenge. Or you can wait till the end of every month and then players are allowed to publish the write-ups for the challenges from the preceding month. So the challenge we're going to look at this time is links 1, and as you can see here the description says, I love linked lists but I can never remember the exact syntax how to implement them in C. Can you check over this implementation and make sure I didn't screw anything up? So we've got a file to download, which I've already downloaded. We've got a server to connect to once we get things working locally. And the description has let us know that basically there's a vulnerable implementation of a linked list that we're going to try to exploit. So I've already made the binary executable. Let's go ahead and check the file type. And we'll see it's a 64-bit LSB executable. It's not stripped, so we'll be able to see the function names and things like that. Let's also have a look at the binary protections since it is a pwn challenge. And we'll see we've got no canaries on the stack, so we don't need to worry about tripping those off if there is a buffer overflow. We've got NX enabled, so we're not going to be able to inject shellcode onto the stack and expect it to execute. And no pi is enabled, so each time the program loads it's going to have the same addresses, which is great. Let's then try to run the binary and see what we get. And we get a segmentation fault. We could try it and run that. Let's do it with ltrace just to see does it give us any hints as to what's happening. And it does. We can see that it's opening flag.txt, and because it's not finding a flag.txt it's given us a segmentation fault. So let me echo fake flag to flag.txt. Let's run it again, and now it's working, and you can see that we can view a list, we can write elements to the list, and we can view time as well. So let's start with viewing list, and it tells us there are no elements. Let's add an element to the list, and it tells us we can give 0 to 0. So let's just try and put in something else. Can we put in a 1? It says no invalid index. Okay, can we put in a character? No unrecognized input. Okay, so let's do 0. It asks us what data we want to enter. We might want to try and enter in a really long value, but there's no problems. Let's try to view the list. And that was a problem, so it actually got a segmentation fault. So it looks like the input we entered was too long, because whenever we tried to view it, it's caused the program to crash. So that's good. We've given ourselves a hint as to what we can look into in terms of a vulnerability. Let's also try and view the time. And we do that and it just gives us the time, which doesn't seem particularly useful, so maybe that's there for a reason. We'll bear that in mind. Let me just try and add some more elements. So just put in an element here, view list, and we don't get a segmentation fault, so we know that it does work if the input's not too long. Let's try and enter in another value. I'm just going to do ABC, view list, and now we've got two elements in the list, 0 and 1. Let's try again and try and edit 1. And notice when we try to edit 1, this time we get this previous, and then there's an address here, and then our element as well. These look quite similar in terms of the addresses, so let's actually go, let's do Python, and can I just do, let me take a copy of this, take a copy of that, and we'll see that the offset is 80. So this previous value is showing up, and then the element is 80 bytes away from the previous address. So there's an 80 byte offset here. Okay, I think that's about as much as we can look at here. We could also, let me just try again, and what do we want to write? Let's write something really long. And notice if we do that, we get a segmentation fault before we even got a chance to view the list. As soon as we wrote something to the list, to that node in the list, we got a segmentation fault. Okay, that's about as much as we can work out without putting this into GDB or opening it up in Ghidra. So I'm going to open Ghidra auto -t for a temp directory and links. This is just going to open the binary, it's going to import it, it's going to auto analyze it and just speed up the process a little bit. Okay, let me move this over a little bit and let's go into our functions, into our main function. We're going to trace our way through this, but actually before we have a proper look at the code, let's just go and review how linked lists work, just so that we know what we're dealing with here. So you can see we've got an example here. This is a single linked list. So you can see here we've got singly linked list, circular linked list, and doubly linked list. And essentially it's quite a simple data structure. We have nodes in a chain or in a list, and each node consists of some data and then a pointer to the next node in the chain. And if we have a look at a doubly linked list, it's very similar. Let me go to the introduction here. Very similar, except we have data and a pointer to the next node and a pointer to the previous node. So if you think about an array in memory, if we want to access, let's say we create an array of 100 characters, if we want to access the 80th character, we can just put in the index of that, but in a linked list we can't do that, and the reason being each one of these nodes could be at a completely different place in memory. So A could be somewhere in memory, and then you have to go forward a long way to get to B, then you have to go all the way back before A to get to C. So even though these are all linked together, in memory they're not going to be in this consecutive order, which means the only way for you to access node D, for example, is to traverse through this list. And if we were doing that with a singly linked list, we would only be able to go in one direction. So if you have a list of 1,000 nodes and you want to access the 500th node, let's say the 750, you have to start off here and go through 750 and check what's the address of the next one, what's the address of the next one, what's the address of the next one, until you get to that 750th node. It does, however, mean you can do things like add and remove nodes from the chain, whereas an array you can't actually do that. You can zero out some data, you can replace data, but you can't actually add and remove nodes from it like you would here. So returning to this singly linked list, if we wanted to remove one of these items from the list, let's say we wanted to remove B, all we would have to do is set the pointer from A, this next node, to point to C. And that would simply be B removed from the list. If we wanted to add a new node here, let's say we had another node down here and we want to put it in between B and C, we would essentially break this link between B and C and say we want B to point to this new node down here, and then we want this new node to point to C. So we remove one link and then we create two links in its place in order to add a node. And that's the general process of how this works. I'll leave a link in the description to a video by Computerphile on how linked lists work, which explains it quite well. An example they give in terms of application of a linked list would be the back and forward on your browser. So if we go back and forward, we can move up and down this linked list, but if I go back and then go and access a new link, that essentially breaks that chain. So that would be a doubly linked list where each node is pointing to the node before it and the node after it. Apart from that, we keep track of the head and we can keep track of the tail. We don't necessarily need to keep track of the tail, but if you do keep track of it, it means you can quite easily add something to the head or to the tail. It's only if you want to insert or remove something in the middle or access something in the middle that you're going to have to traverse through the list. There's the circular linked list as well here, which I didn't show, but here's a quick diagram just showing that as well. Alright, so let's go and take a look at this in Ghidra and see how they've implemented it and what sort of vulnerabilities there might be in the code. So starting here from the main function, we can see that it does open this flag.txt. If it doesn't exist, it's going to crash the program. That's what happened to us at the beginning. And then it's going to read, you can see into this variable, it's opening that up as a file pointer, and it's reading from this file pointer a %s, so the format is a string, and it's reading it into flag, which is part of the BSS section. So that's worth bearing in mind. This is opened at the beginning, and then we go into the menu. The menu asks us, do we want to press 1 to view the list, do we want to press 2 to write a new item to the list, or do we want to press 3 to view time? So we could start off at the view list. Let's go and have a look. It looks like it's just going to loop through. We could start renaming some of this stuff. I like to change the loop counters and stuff. So we can say that's an I might change that to J, just because I don't like having the long variable names that don't really add anything. But it's just going to loop through anyway. It's going to print those out. That's fine. Let's go back to our menu. And the second option is write. And this is where most of the code is. So I like to try and trace through some of this and rename variables and add some comments to understand what's going on. We can see at the beginning we have this if statement, and it's got this local 30, that's our menu input. So I'm going to change that to, in fact I'll change that to index. And that's asking us the index, and it's basically checking to make sure the index is valid. So we're only allowed to access nodes that exist. We can't go and try to modify node 5 if we've not got any nodes in the list. That's fine. Provided we put in a correct index, then it's going to check, is the index 0? So essentially it's checking here to see, is the index the head node? Are we trying to add the first node, or are we trying to modify the first node? So again, I'd probably go here and say add/modify head node, and note that I'm just doing a semicolon to open that up as a comment box. We can go and start renaming some things in here as well. One thing I'll mention as well, actually, if you're not sure where to even start renaming things, note that down here we have this printf, and we can actually see what it's printing. So it's printing local2 as the I variable. It's printing this previous value is local 28, so I can just literally go and say, alright, this is I, this is previous, and this is element. So they've actually told us what the variable name should be here, really. So that's made that bit a little bit easier. Let's go up and see what else we've got here. So this was add in the head node. We can see that we've got this is set to global list. I'm actually going to change this to be the head. And we can see that basically it's going to make sure that if it doesn't exist, it's going to malloc 48 in hex, which is 72 bytes. It's going to malloc. It's going to increase the max length, so it's going to increase the length of the list. And then it's going to call write data, and it's going to write the head. So write data is literally, let's have a look. So it's going to read 100 bytes into the parameter that's passed. Now, remember that the variable, the malloc, is getting 72 bytes, and we're reading in 100. So the fact that we got that segmentation fault earlier is probably related to the fact that there is a buffer overflow in that write data function. Okay, and the second if statement then is checking if the index is max length. So the first one was saying if the index we provided is 0, then we're talking about the head node, the first node in the list. If the index selected is the maximum length, so the last element of the list, obviously we're dealing with the tail. So this is going to add something to the tail, and then that means that the last thing is modifying something in the middle, because remember that whenever we did this manually, which I always find to be quite useful, is to actually run through these things and see how does what we're seeing in the program match up with the code. And remember, the only way we got it to print out this previous and element value was by modifying a node in the middle of the chain. So our first segment is adding or modifying the head node, our second segment is adding the tail node, and the third segment is modifying a node in the middle. So let's go and update these other variables as well. We've got this one is adding to the tail. So essentially what's happening here, you can see this local 18 is being set to head, and then what's happening is it's looping through from head. You can see this here, 40. So it's moving along every item of the list until it finds one that is empty. So it's basically going through until it gets to the end of the list, and then it's going to create a new element. So this, let me change that to tail. So it's setting tail to head, it's looping through until the tail is actually the end of the list, and then it's going to set this, let me rename this to next. This is next, so it's moving through the next node, next node, next node, until it gets to a node that's empty, an empty chunk of memory, and then it's going to say the tail is now that empty chunk, and now we can set the tail to be the element, to be the data that we're writing, and then it's just going to write that data. So again, let's do add node to tail. Let's apply that. We could say here we are traversing list from head to tail. Oh, let me sometimes put these in the wrong places. Let me change that. Set that there. No, that still wasn't it. Set it here. There we go. So we're traversing the list here, and then we add the new node to the tail. And then we could also say we're writing the data here if we want. So we're writing our new node. Oh. Alright, that'll do. And then finally, we've renamed these already because we had the print options. We could also just change this and say, alright, so this is add node in middle, or change node in middle. And we're gonna, again, we're setting the element here to the first element, not to the head. We're setting it to the first element past the head. And then we're looping through all of the items until we get to the correct index. You can see here, once the index is correct, we've got to the correct node, and then we basically modify it. We set the previous to equal the current element, and then we add our new element there. Hopefully that makes sense. I'll not bother commenting this, but you could basically put the same comments here as you know, down here, just to match that as well. So what is the vulnerability here, and how are we going to exploit it? Well, a couple of things came to mind whenever I was going through this. One is we've not really looked at this view time option. Let's have a look at it. It's got system and date. And quite often here, let's look, the date is at this memory address, 4020FA. It's in the .data section. So quite often when you have a challenge like this and it has a call to system, the goal is to overwrite this address. So let's say we were to overwrite this date string with the string /bin/sh, and that would mean that whenever we try to access the time, whenever we try to view time, it's going to call system/bin/sh instead of system date and give us a shell. So if we wanted to do that, let's go back to our write function. If we think about that in terms of those previous values, whenever we printed the previous value out here, well, the previous value, or each node, is pointing to the next node essentially. So if we were to overwrite one of those addresses and say, rather than pointing to the node where we've put in our name or some data or something, have that point to this address in the .data section. So let's overflow that variable that we have so that the previous address is going to point to date, and then let's make sure that the value in there is /bin/sh. So let's go and see how that looks, but what I will just mention first of all is, whenever I thought that, the first thing that came to my mind is, why open the flag? If the goal is to change the string that's being passed to view time and have it get a shell, why even open the flag? If we're getting a shell, we can just get the shell and then read the flag anyway. So that kind of was a bit of a hint that this probably wasn't the right direction to go down. Typically I like to check things out in GDB to see how they look manually. In this case, I'm going to open up a PwnTools script because we need to supply the address of the date string in the .data section. Where is it? We need to supply this string, and we can't enter some of these characters in ASCII, so we need to use PwnTools or Python to do that. So I'm going to paste this in, and essentially all we're doing here, we're adding three elements to the list. So there's our input, our index, our menu option, our index, and then the data that we're inputting. And once we've got 3 elements, we can now modify the element in the middle. So we're going to say we want to modify the middle element, the index 1, and we want to supply 64 bytes of data, and then we want to overwrite the link. So we want to overwrite what's pointing to the next element. We want to overwrite it with the address of the date string in the .data section. So that's exactly what we're doing there. We're just flattening it into its 64-bit format, and we send that off. We're going to go interactive at the end just so we can have a look at it and see what it looks like. Let's do Python exploit. We run through that, and now let's view list. And notice what we've got. So we've got our bin.sh, which was our first input. We have the long string that we put in there, the 64 A's, followed by the address of the date string in the .data section. And essentially what we've done is we've overwritten the link to our third note, which should have been bin.sh as well, and it's now pointing to date in the .data section. So I kind of thought this was all looking good. I thought now if we can just overwrite this date with the bin.sh string, we'll now be able to get a shell. And to do that, let me go back to the script. Essentially, just want to add another item to the list, or should I say modify the item, and the item we wanted to modify was the second index, well, the third item, second index, and we want to overwrite that date string then with the bin.sh string. And then we want to view the time. Let's do it like this. Let's run Python exploit. We run through that and you can see that it crashed, and we've got, what have we got in here? The element is, oh, it crashed whenever we tried to send the bin.sh. We had an end of file there already. We can unhex that, and that is list ma. Note that it shows I is 1 for all three of these as well. So I'm not actually too sure if it's possible to solve it this way. I thought that whenever I ran this in GDB, let me do that again, let me do it like that, Python exploit, that's the same output, okay. So yeah, I'm not sure if this is a possible solution, maybe I just didn't do it right, or whether it was just a rabbit hole, because obviously that system date call has been left in there either for a reason or just to add a bit of confusion, I'm not too sure. So the other option is the flag. The flag is loaded into memory, and then it's also read into this variable as well, into this file pointer. Sorry, it's read into the file pointer, and then it's read into the flag section here, which we have the address of. We could verify that. Let me open up GDB-PwnDbg links. Let's run the program. We'll hit Control and C, and then you can do search-s to search for a string, and then search for our fake flag. And we can see it's in a couple of places. It's on the heap right here, and it's at the same address that we see here in the .data or the .bss section. Which means, why don't we just try, rather than trying to overwrite anything, why don't we just try and set one of our items in the list to point to the flag, and then whenever we try to view the flag, we'll hopefully be able to read it. So let me copy over another script. I'm going to close this down, paste this in, and it's very similar here. I've just optimized this a little bit, so we're looping through 3 times and creating 3 notes, and then we're going to modify the middle note. We're going to do our 64 A's and then follow that with the address of the flag. And now, hopefully, this element, this item of the list, will be now, well, the next item of the list will now be pointing to the flag. So whenever we try to view the flag down here, hopefully it'll be displayed, and I've just added some. We know that we want to ignore the first 2 entries because the third entry is the one that's going to contain our flag, because we're modifying the second entry to say instead of pointing to the third entry, we want you to point to the flag. So the third entry should be the flag, so we'll try to print out the third entry and see what we get. Let's do Python exploit. We run through that, we get fake flag, which is great. That means we have printed the flag, and now all we need to do is try it against the remote server. I have the server address and port number here, so because I'm using this pwn template, which you've probably seen me bang on about a lot, you can quite easily swap between GDB, remote, local. You can set up breakpoints and stuff here. So that means that all I have to do is type remote in capital letters, paste in the server address and the port number, run the exploit, and we get back our flag. So let's just have a quick recap of the LinkedList implementation they used and how we were able to exploit it. Each time we add a node either to the head or the tail of the list, malloc is called to allocate 72 bytes on the heap, so it's going to return the address of that. The head is actually part of, I guess, the .data section or .bss section, so that's where that address is going to be written, the address of the chunk on the heap, and the list length is incremented. The same happens if we add a node to the tail, but notice that whenever that happens, we allocate 72 bytes from malloc, and then 64 bytes into that is set to 0. This is basically setting the tail, it's basically setting the last node to point to nothing, to point to 0, because each node in the list points to the next node, except the last node, which has no node to point to. So that's set to 0, and that's why that happens. And whenever we're looping through each of the items, we're not looping through the 72 byte chunks, we're looping through 64 bytes at a time, because it's 64 bytes for our data, and then it's 8 bytes for the address of the next chunk. And that is where the vulnerability is, because whenever we get down to add a node in the middle, there's nothing to restrict us from writing more than 64 bytes of data, and we know that it's going to take 64 bytes of data, but the next 8 bytes is supposed to hold the pointer to the next chunk. And if we overwrite that with the address of something else in memory, then that next chunk now points to whatever we've told it to point to. And in our case, we told it that we wanted it to point to the flag location, which was set right here at the main function. So we know that this was opened, it was read into this location, and we were able to set the address of the chunk to point to this location. And then whenever we go to view the chunk, obviously this is the location it's going to read from. And that's going to wrap it up for this video. If anybody solved this in a different way, particularly if anybody got a shell by using the viewTime function, I'll be interested to hear about that. If not, if you have any questions or comments, leave them down below. Thanks.